first of all, this is my first seminar since. Okay, I'm having problem finding my pocket. Okay, can you hear me well? Okay, this is my first seminar since 2019 September, I guess. So yeah, with this microphone, my voice I think I'm finding to be a bit shaky as well. I'm not accustomed to giving seminars nowadays. Now, thanks a lot to Supratikda. And okay, before that, all of us, I think most of us, I think, whom I have met since morning, said that this is their first experience as well after pandemic. So thanks a lot, Supratikda, for bringing us out of our cocoons and making it an in-person seminar, an in-person workshop. It is a beautiful workshop, and I'm really happy to be a part of it. Okay. Before I start my talk, apologies that 21 centimeter cosmology in the square kilometer era, I am not going to talk about 21 centimeter cosmology, I am not going to talk about SK. Yes, I have one work with 21 centimeter, but that is on constraints on primordial non-Gaussianity. That is that I did with Topomai Guha Sarkar. That was a few years ago, but that was constraints on primordial non-Gaussianity. I'm going to talk about reionization history, and most part of it is going to dwell on cosmic microwave background. Okay, so by joining bits and pieces of reionization history, I mean that there are different information about the reionization in different observations. One part you can say the cosmic microwave background, the polarization mainly, and also the temperature, where there are degenerate effects with the amplitude of the primordial power spectrum. I'm going to explain that. And I'm going to also talk about UV luminosity densities that I'm going to use as a data to constrain, and also the QH second data, the free electron fraction or the neutral hydrogen fraction that are there in the universe, and we can detect it from quasar data. Often these data are criticized as model dependent, and sometimes since they are only made with only one observation, some of these data points are not averaged over the different sight lines as well. So, but anyway, so my job in this talk is going to use the most of the data that are available there that we can use in a conservative theoretical framework. Okay, and why I'm saying conservative theoretical framework, because our inferences that we can make from the observations, they depend on the model we choose. Okay, and at some point of time, if your observation is pretty constraining enough, then at some point of time this dependency goes away from the summary statistics. I'm going to explain those. Okay, you have seen this in many talks since the morning, but I'm going to describe it nevertheless, because I will need certain features of it that has not been discussed. Okay, so you know that in the primordial phase of our universe, this is the timeline of the universe, we had this inflationary epoch. Okay, and by inflation we generate the primordial seeds of structure formation. We get the primordial power spectrum, and the primordial power spectrum can be explained that can be constrained till date is by two parameters. One is the amplitude, and second is this famous spectral tilt. Okay, which is of 0.96, and the primordial spectral amplitude is of the order of 2 × 10⁻⁹. Okay, they are unit dependent. Now, why I'm saying that? Because when we are talking about CMB and we are trying to constrain the reionization history from CMB, it becomes degenerate with the information that you are feeding into it, or feeding with the cosmological primordial power spectrum. If I use a different primordial power spectrum, the tau, the optical depth that you infer from cosmology, from CMB, might change. Okay, so there are degenerate effects. So after recombination, there were a few other things that happened. At some point of time, neutrino became non-relativistic. Okay, so at some point of time, neutrino were non-relativistic. About I think 2 mega electron volts, it became relativistic, and then at some point of time, when their momenta dropped, what happened is that neutrinos stopped being relativistic and their energy budget contributed to the matter energy budget, okay, omega matter. And that actually took part in the expansion of the universe. So the more neutrino that are there after, let's say, 100 redshift, it depends on the neutrino mass. We have not been able to detect it. But if, let's say, it is 0.06 electron volt, the sum of them, it is of the order of 100 or so, 100 redshift. So from then, the neutrinos started to take some effect in the matter-driven expansion of the universe, okay? Omega matter times a to the minus 3. So now you know that the one particular statistics of importance in the field of reionization is the optical depth, right? Which is the integration of the electron density multiplied by the Thomson scattering cross section along the line of sight. And there you have a line integral, and the line integral can change if your matter content or dark energy content or any of these changes, okay? So neutrino also can take part in your determination of the optical depth or other quantities related to reionization that you are planning to take from the CMB, okay? Of course, in other cases, when you are talking about the QH second observation from the quasar data, Lyman alpha forest damping wings, etc., Lyman alpha emitters data, those things does not play much strong role, very subdominant role, but from CMB, it is, we find a strong or significant role till certain point of time. I'm going to show you when that point of time was there and after when that neutrino part stopped contributing as well when we had more information, okay? So during the matter dominated phase, as we know, the process of ionizing hydrogen, helium atoms in the intergalactic medium is by high energy photons is called the reionization, okay? We all know about these things, and again, I'm not going to talk about 21 centimeter. I'm going to talk about the observations that are that has already happened. We have the data, and we can constrain the reionization with that, okay? And now the thing is that parameterization or modeling is very important in doing physics. So if you do simulation as well, there is an underlying model that what quantities or what rules you are simulating the universe with. Is it lambda CDM? Is it having some dark matter with some interaction, etc.? Does it have a spurious dark energy component that is actually interacting with the dark matter, etc.? So those things come into play. So here also, in order to understand reionization, you need to parameterize, and the parameterization can happen in few ways. For CMB physics, the people who work in CMB, they do not talk much about the sources of reionization. They talk about the free electron fraction as a function of redshift, okay? The XE as a function of Z. Why? Because they need to know the tau, and from tau dot e to the power minus tau, that is called the visibility function. And the visibility function actually is a probability distribution that we use to calculate the recombination error. That is same thing that we use in the CMB as well. So they just use certain parameterization in the XE. And the most famous parameterization that people use is from this paper, and that is what we use in Cosmo MC or class. If you have run these codes, it assumes a tan hyperbolic or a symmetric model of reionization, that it was 0 at some point of time. Okay, before class and Cosmo MC, I think in CMB fast era, I have not used CMB fast, but I heard that it uses a perfectly sharp or perfect step model of ionization history. But here they use a tan hyperbolic model with a width. However, for all purposes, they fix the width. For example, when we talk about Planck constraints, the width is fixed to be delta z equal to 0.5, okay? And the functional form is also fixed. So the baseline model uses that. Now, before that, Wayne Hu and Gil Holder, they discussed about doing a model independent analysis, and they proposed this principal component analysis, okay? Principal component analysis tries to find the most dominant eigenvectors, and using that, they constrained the reionization history, and later on, Wayne Hu's student, Cora Vorkin, Chen Hendricks and Mortensen, they worked a lot on these topics. One of the big problem about this parameterization is that it does not respect the physical boundaries. That means that your electron fraction cannot go below 0 or above 1, but PCA does not respect that. So they sometimes restrict the parameter space, but doing the restricting the parameter space makes some other complications in the Markov chain Monte Carlo as well. Okay, your posteriors might not be very smooth or something like that, and your inference might not be very robust. We came up with a model which we call poly-Reyon, and that there we propose that we will take some nodes. We'll take some nodes in the redshifts where we have observations, okay? And we said that this amplitude or the value of electron fraction in these nodes can vary, can go up and down between 0 and 1, all right? And I'm talking only about hydrogen reionization. For helium, we can simply add a factor with that. That we have taken tan hyperbolic because we didn't have any other data to constrain. So there we basically worked with this model. And as I said, Chen Hendrick has, with Wen, who has done this work as well, where they have modified the thing a bit, the PCA formalism a bit. And after that, this paper came, Milia and Boucher, which basically used this model, my model with George, with, as I said, that we had certain nodes that are fixed because we do not have data to vary the nodes. So they added this parameterization or this flexibility that the nodes can vary as well. And it is like an old wine in a new bottle, but they named it as a flex knot, and that has been used in the Planck 2018 analysis. Okay, so that uses actually the piecewise cubic Hermite interpolating polynomial that respects the boundaries 0 and 1 because it is a safe preserving function. Okay, moving on from there, people also work with parameterizing the source and the sink function because reionization is a competition between ionization and recombination. So if you can parameterize these two, their time evolution, then you can also understand many other aspects that you cannot understand from here. And of course, you can do derivatives there and you can derive the other parameters, but again, those will be dependent on whatever you are choosing for the recombination, the clumping factor, etc. So this is where many works have been done. Saurabh Mitro, Tirthankar Roy Choudhury and Andrea Ferrara, which is basically dependent, heavily dependent on the semi-analytical modeling that Tirthankar Roy Choudhury and Andrea Ferrara did a long time ago, which is basically taking the overt density derived from the power spectrum, matter power spectrum, and then going to the log normal space and understanding the main, okay, it is a semi-analytic modeling, it is not dependent on simulation as such, but it has the physical things that are the power spectrum, okay, that you start with a power spectrum that is derived from CAM, etc. So here many physical inputs are there. So there we also try to do some work here in parameterizing source and sink function. What we did is that the source and sink function, we made it completely arbitrary. We said that we do not know what this is, and basically keeping two endpoints, we allowed them to vary between different nodes, and here also definitely we wanted the node to vary, okay. And of course, there are numerical simulations that are there. Many people have done many works. I have just quoted one, but there are many works on simulations, okay. Shumon has many works on simulations, and I guess Girish has done many works on simulation on understanding the reionization history. And there are many people in the room who have worked on this. I think Samir has done a huge amount of work on this. Okay, so to recap some history, let us see how the CMB story can tell you from WMAP or pre-WMAP era to Planck 2018. Okay, as I said, in the CMB community, the most common practice is to parameterize the ionized hydrogen fraction, okay, or the free electron fraction. Okay, tan hyperbolic model is used, and this is the another one. But this is this term that you are seeing, the optical depth. does not uses this information, okay, the source and sink function, that just uses this tan hyperbolic model. Using that, WMAP 2003, which is WMAP first year data, I believe, came up with a very big tau, which made lots of chaos because it was not consistent with many of the other data sets, I believe, at that time. But then it came up with, they came up with the polarization data in 2005 and then 7, and in 2013 they released the WMAP 9-year data, which reported a value of tau of 0.081, okay, with this error bar. At some point of time, Planck, right after that, Planck came, Planck 2013 was there, but Planck 2013 used the WMAP polarization data to constrain the tau. Planck 2015 came up with the low L polarization data from the Planck observation, but it was from the low frequency instrument. So you can see that the error bars are very close to each other. Although the data, okay, the tau value that you can obtain from there are different, 0.081 and 0.066. They were actually not inconsistent, okay. But then came Planck 2018, okay. It had this 2018 high frequency instrument data. I think best person whom you can understand from is Tuhin Ghosh in this room. So they basically came up with this map with high frequency instrument, and you can see that the error bar reduced, okay, nearly by half. The error bar is 0.007, okay, and as well the mean value of tau decreased. All right, so you can see that now it is inconsistent with WMAP. So Planck and WMAP are inconsistent in the value of in the determination of tau. Definitely, these inconsistencies can point towards lack of an original model, let's say original modeling. But anyway, who knows? It can be systematic as well. There are many papers that has been written. There was a data called SROL2 as well that has come up with. I'll just discuss the results later. Okay. But anyway, so where does the most important information from CMB comes in the comes in the field of reionization? First, there is this temperature anisotropy power spectrum. However, I do not call it a most important information because that part is completely degenerate with the amplitude. What happens is that if you have free electrons, they are shielding the photons and your intensity drops. And now, if I say that, okay, my intensity didn't drop, my primordial power spectrum had lower amplitude to begin with, right? That means that we cannot say for sure that whether this effect, whether the power spectrum, angular power spectrum that we are seeing is an artifact of the low primordial power spectrum or a high optical depth. So that is why the main parameter that we can constrain is A, the primordial power spectrum amplitude, times e power minus twice tau. Okay, that is what we can constrain. But the most important part comes from here. Okay, when the photons or modes, let's say the wavelengths, were entering the horizon during the reionization era, they were filling those electrons and they were scattering and having Thomson scattering, okay, and that scattering polarized the light, okay, that gives rise to E mode polarization, and that amplifies this. Okay, it is 2015 release, by the way. I'm going to compare that with 2018 release as well. So you can see that this is the best fit, and these are the data points. Okay, so let's say we had an early reionization. How will we understand that there was an early reionization? I can say that, okay, the photons that entered here would have seen this effect. So I would have seen a plateau from here. Okay. So if let's say the reionization started from redshift 30 or something like that, we would have seen this hill that is coming here would have started from here. Right? There is a Z to L relation and things like that that you can simply compute. Okay, so that is one part of the information that you can get from the CMB. The second part of information is coming from the QS2, and where I said the one big controversy is there. Not the controversy, there are criticisms there. First of all, these are very low redshift observations where reionization was actually completed. Okay, so we cannot use them. These are Gunn-Peterson optical depth, Fan et al. These are few seminal works, but these are implying post-reionization scenarios where reionization is nearly complete. But there are dark gaps in quasar spectra. There are many experts working on these. Lyman alpha damping wings. There was at some point of time this redshift 7 determination of a quasar by, I think, just a second, Daniel Mortlock et al. So that give rise to certain constraints on the QH second or the XE, the free electron fraction. This is the volume filling factor, by the way. So this is something that we can use in combination with CMB. So this is what I'm doing. I'm basically collecting these bits and pieces. At some point of time, I'm planning to join them. Okay. So we first try to use this free electron fraction parameterization. As I said, we had few nodes. As you can see that I am using these nodes, the redshift 6, 7.5, 10, and 20. Okay. So 20, why 20? Because 20 there is no data, but actually it is going to see the integration from the CMB, and I am not using any summary statistics from CMB. Okay, this is a very important point, that you should not always use the summary statistics from CMB because that is biased towards one particular construction, that is the tan hyperbolic model of reionization. Okay. So you should feed the angular power spectrum data directly. Now, what does it say? That if I do not use any, optimistic means that I have used the QH second data as well. Conservative means that I have not used any QH second data, I have just used the CMB data. As you can see, it was the time of 2015, 2017, but at that, by the way, there was already 2016 paper, Planck paper came in, but the data was not public. So the data that was public was 2015, so we could work on that data in 2017. So these are the constraints. You can see that we cannot see much constraints, but one thing that you can see that at z equal to 20, there is a slight peak which is nearly of 1 sigma significance. It is showing that probably certain fraction of electron were there, free electrons were there. Now if I use this other data, what you can find is that at redshift 10, it says by almost 3 sigma significance that you must have some non-zero XC which is of the order of 0.2. Okay, 20% electron fraction will be there, 0.2 electron fraction will be there at redshift 10. Okay, redshift 20 we cannot say more than 2 sigma or 1.5 sigma or something like that. So what we find is that Planck 2015 data was actually supporting extended ionization history. Now, constraints of the optical depth, if you find it from here is this, and if you find from here is it lies like around 0.1. However, it is here you see it is about 0.09 and this is 0.1. If you use tan hyperbolic model of reionization, can you see what Planck 2015 was suggesting? 0.066. Okay. Now let me see my results. One is at 0.09 and one is at 0.1. And at the same time, there are two questions that you have to ask. Is this model better? You can do it by chi-square analysis, you can do it by Bayesian evidence analysis. And at the same time, you can say that whether this value is good. Of course, if it is, if chi-square improves, if your model has preference, then of course you should trust this value rather than the value that you are getting from tan hyperbolic model. This is what I wanted to stress from the beginning, that if you have a full data, you just don't use the summary statistics. You use the full data and use your model to constrain it. Okay. So constraints are dependent on parameterization. Okay. Change in the parameterization leads to change in the summary statistics, the optical depth in this case. There are many other things actually that can happen here. It is not just the reionization history. The value of H0 can change if you change the model. Okay. Many other things, sigma 8 and all these things. Conservative bounds, what I did is that I have just collected samples from 2 sigma and I have plotted them. Okay, you can see it here, and samples from 2 sigma again I have plotted here. As you are seeing at around redshift 10, it is saying that within 2 sigma I do not find any histories that are saying that it is the reionization was hasn't started by redshift 10. So it is of the order of 0.2 as you have seen. We are finding it here, the mean value. Around that there are some width, okay, there are some scatters. Okay, now we called it polyreion, and as I said, this is for publication, I mean this is for advertisement as well, and it has been used for several publications and also in Planck 2018. Okay, now let us come to degeneracies, as I was saying. Okay, degeneracy is a very important topic. First of all, this delta Z reionization is something that is saying that the width of the ionization or the time of the ionization where the universe was 10% ionized to 90% ionized. Okay, we take this Z1 and Z2. So Z2 minus Z1 is basically this delta Z reionization. Of course, you can understand that the delta Z reionization, if you it is going to be degenerate with tau, the more the redshift, the more the redshift of reionization, you keep on integrating and you get higher value of optical depth, but it is not in all the cases because the XE as well plays a big role, which comes in the CLEE power spectrum. Okay, if you use a forecast, okay, if you just use a light bird like data, you know light bird is going to go to space in few years, maybe 5 years or something like that. And it is going to be a cosmic variance limited observation in temperature and polarization up to L equal to 800. Okay, so since it is cosmic variance limited in polarization, remember Planck is cosmic variance limited in temperature but not in polarization. So at low L it is going to be cosmic variance limited. So since it is cosmic variance limited, it is going to constrain tau much better than Planck, and it is going to break the degeneracy. At the same time, as I was saying, that there is a degeneracy between the primordial power spectrum and the tau, because you have seen this bump, right, at CLEE. Now imagine I change the primordial power spectrum, instead of red tilt I try to make it a blue tilt. So there will be changes in the inclination angle, etc., in that particular graph, and I can make it degenerate. I can make a degenerate effect with the NS as well. So you can see that there is a degenerative effect here as well. However, with with core and light bird, we can break that degeneracy as well. You might wonder that why we are not able to, constrain NS better than Planck in light bird. That is because Planck, the light bird's resolution is not better than Planck. Its sensitivity is better than Planck, but its resolution is not better than Planck. As I said, it is cosmic variance limited, but only up equal to 800. All right. Now, neutrino mass. Okay, so neutrino mass is something that I said that it contributes to the energy budget in the matter sector during the reionization epoch. So it is going to be degenerate as well. Okay, unless you break the degeneracy with a very good probe of low LEE. Okay, so this is with Planck 2015 data. Similarly, we tried to do a forecast with light bird and core. We found that the degeneracy can be broken. All right, and there is a simple pictorial description as well. Okay, another thing is that I am not talking about this because we do not know whether dark matter annihilates or not, so I am not going to talk about that. It is also degenerate with the dark matter annihilation to some extent. However, with the Planck low L data, we have been able to break those. I am coming to that in the next slide. Okay, so the bottom line is that keeping the same optical depth, if we assume the total mass of neutrino to be higher, let's say it is not 0.06 electron volt, it is let's say 0.1 electron volt. Maybe it is ruled out. No, it is not ruled out. 0.1 is not ruled out yet. So then, due to the change in the expansion history, we need a longer duration of reionization. So that is what it is showing. Okay, this is where it is coming to be very important. And then what we can do is that we can break this degeneracy. We can break this degeneracy in light bird itself because it is going to detect the low L. But in the core, with light bird, we can do like this. Okay, we break the degeneracy, we constrain the delta Z reionization, the reionization width or the total redshift of reionization, duration of reionization, but we cannot constrain the neutrino mass better than Planck because it is not capturing the low L signatures. Neutrino mass also had low L high L signatures, which is oscillatory. Okay, so at small scale, neutrino mass gives an effect, which is not seen by light bulb, but which will be seen by core. So, core can detect neutrino mass if it is within certain thresholds. So, either a CV limited, cosmic variance limited large scale polarization explorer like light bulb or an observation with better resolution, core or CMB Bharat or PICO will be able to break this degeneracy. Okay. Okay, fine. Okay, now it comes to the degeneracy with the large scale suppression. As I said, now let us say the parameterization of the power spectrum does not depend on just two parameters. Okay, not just not just NS and AS. I say that okay, there is a suppression in the power spectrum. Let us forget all this thing about this. Okay, so let us say that we add a suppression. In 2010, there was a paper saying that if you have large suppression in the power spectrum in the TT power spectrum, it can be degenerate with the EE suppression, and that can be degenerate with the reionization history, and the detection of these features, detection of this suppression can be reduced by 2.5 to even 5 sigma depending on what type of observation that you are looking for. We redid the analysis in 2017, and we found that the suppression which is given by this parameter, let us not talk about this is called Wiggles. Okay, the suppression that is given by this parameter, okay, this suppression, then for that with tan hyperbolic history we get this constraint, and with a different reionization history, an extended reionization history, the contour degrades but not more than 1 sigma. So this is no longer true. The data that we have, the suppression in the power spectrum does not, suppression in the power spectrum that you are getting from the TT data does not get contaminated by the EE to an extent more than 1 sigma. Okay, maybe it is 0.5 sigma or something like that. Now Planck 2018 came after that. Okay, let us put this two in perspective. So this was Planck 2015 best fit. This is Planck 2018 best fit. Immediately you can say that the height of the peak has reduced. Okay, so height of the peak has reduced. So there has been lots of things. One of the best thing that happened is that it was able to break the degeneracy. We didn't have to wait till core or light, but it has been able to break the degeneracy between neutrino mass and tau, or neutrino mass and the duration of reionization between Planck 2015 to here. It is like this. So here we are using Planck 2015, Planck 2018 with tan hyperbolic, and 2018 plus BAO. Okay, so there are different observations that we have used to constrain the data. Again, here we are not using tau as a summary statistic. This is very important to say. Okay, the last bit of, now this was CMB and UV luminosity data. By the way, here no QH second data were used. Sorry, I did say UV luminosity data. I haven't come to that yet. Okay, now we have just used CMB data here. Earlier in some works I showed we had used the QH second data as well. Now I am going to add one bit of information there as well, the UV luminosity data. So I missed Girish's talk, but I heard from another talk that Girish has talked about this one. So you know this, therefore I assume that this is the UV luminosity density data, okay, as a function of redshift. There are different works. So we have tried to use the work from, Ishigaki et al. Abje, this paper. Okay. There are papers by other groups, Robertson et al. That also comes near, the results are comparable, but we have used this one as they were more recent, and we could get our hands on to that. Okay, so these are actually you integrate the luminosity functions to different magnitudes. So you can say that this is a very optimistic magnitude truncation, and this is a conservative magnitude truncation where you have at least seen some galaxies up to minus 17 magnitude. Okay, so we use that, but in order to use that, we cannot now use the XE. Okay, XE is basically the free electron fraction. We have to use the source and sink function. This part, the end ion dot, okay, the source term is actually a product of 3 terms, or integration of 3 terms, you can say. The luminosity density photon production efficiency and the escape fraction from the galaxy to the intergalactic medium. Okay, there are few steps involved in that as well. You can break it to different other two other factors as well, but yeah, I have not worked on that, so I should not comment on that. And the sync term, which I call sync term, is basically the recombination. It depends on one parameter, the CH second, and of course the temperature, but it is not much dependent on the temperature. From several papers, you can find that the IGM temperature is of the order of 20,000 Kelvin, so you can use that. Even if it is 30,000 Kelvin, the result does not drastically differ. That can be seen from the observations. Okay. Now, these are the works done earlier that uses one particular type of power law model in the UV luminosity density, certain power law you use, and then you constrain the data. Okay. Now I am going a little bit fast. I thought that I will be finishing in 30 minutes. Okay, but yeah, I was clearly, I mean, not thinking correct. So now there are. What we try to do is that instead of using this power law model, we try to take a free form solution. Okay. So the evolution of the source and sink terms are described by a few freely varying nodes. Okay, you can now you understand the nodes, that you can vary the nodes and the amplitudes in the nodes can vary. That goes in the Monte Carlo simulation, and they are connected with piecewise cubic Hermite polynomials to preserve the shape. And starting from a high redshift, the ionization equation is then integrated and compared with the data. We integrate it, feed it into CAMP, and then we compare with the CMB data. Now, why this is important, why freeform solution is important, is that it is not biased towards particular phenomenological construct. Of course, there is a part that we are missing from the simulation, but we have seen that actually the result that we find from CH second or something like that, that matches with simulation pretty well. Then solving reionization equation provides the realistic ionization fraction. As I said, constraints are conservative. Because you are allowing lots of parameters to vary, and physical parameters can be obtained in post-processing, and I already said why complete CMB data is needed, okay? Because your inferences on summary statistics will be dependent on your model. We have used these three pieces of information here, Planck 2018 or 15, we have done both. UV luminosity density from Hubble frontiers field, that is given by Ishigaki et al., their compilation we have taken, and QH second data, some of the QH second data we have used, Franning redshift 6 to 8, okay, and these are the results. Okay, these are some samples that we had plotted, only Planck 15. If you add UV luminosity data up to 17, okay, UV 17, if you add QH second data. So basically what you see that it is constraining more and more when you add data sets. Again, there was the Ishigaki et al. 2015 paper, they said that the Planck constraints are in tension with the UV luminosity data that they are finding. But again, that is dependent, that interpretation is also dependent on the model that you are going to use. If you use a freeform model, of course the error bar increases, but you find that even with a lower parameter model, we find that there is a consistency, but it is not as good as with Planck 18. This is with Planck 18, okay. The green one is 2018, only Planck. The blue one is with Planck plus UV 17, and this one is with Planck plus UV 17 and QH second data. Okay, and these are actually the top panel is not visible. So we had different nodes B0, B1, B2, B3. So different beans. Okay, the number of degrees of freedom increases as you increase the beans, and these are the results. Okay. As you can see, with Planck 15 is now completely consistent with Planck 18 as well, okay, just by using a different parameterization. If you use tan hyperbolic parameterization, there are inconsistencies between two versions of the same observation. Now, if you use a different parameterization, they are consistent. So clearly there is, I am giving you a hint that tan hyperbolic parameterization is not a good parameterization. In fact, let me make a bigger statement that any symmetric parameterization is not a good parameterization for the reionization history. Okay, and again B0, B1, B2, B3, the electron fraction looks like this. The constraints on electron fraction as you, and again you can see the inconsistency. This is the tan hyperbolic model. Okay, so it is not even coming within 2 sigma for most of the histories. This is the most tightest constraint that we have obtained, and tau value that we have obtained is 0.051 plus minus 0.001. This is even better than the cosmic variance limited CMB surveys that you can find is 0.003 or 0.004 that you can find best from the cosmic variance limited survey. Anyway, you have to take this result with a pinch of salt, because again, as I said, UV luminosity density, though we do not have enough measurements for QH second data that I have used, they are not space average, sorry, angular average, and they are sometimes model dependent, although not this model dependent, but with different model you can find some different things. We have tried to cut down the results, cut down different QH second data, etc. We have found that our results are pretty consistent, but again, I would say that you should take this result with a pinch of salt. One important thing that, of course, if you go to higher parameter space, okay, this is the least, this is our baseline model. This is with 1 node, 2 node, and 3 nodes. You can see that with more nodes, you are basically adding more parameters to parameterize the source and sink functions. Of course, the chi-square improves, okay. This is 2780, 2778, okay. The chi-square improves, but it is not sufficient, okay. 2790 to 2786. It is not sufficient with respect to the number of parameters that you are injecting in the model building. So the log B is actually going down. In Jeffrey scale, this means strongly ruled out, and this means decisively ruled out. Okay. So those models, it says that Planck 2018 data actually rejects these models. Okay. Any complicated reionization history is rejected. You can simply see it from here. Only with Planck you are seeing so much possibilities. These things were entertained by Planck 2015. As Planck 2018 came, there are not more choices anymore. 2015, 2018, you see the 2-step reionization, 3-step reionization, early reionization scenarios all got ruled out. Okay, I am just crossing time. I will just take 2 to 3 minutes, okay, just to show 2 important results. One is that in the first work we tried to work with the efficiency factor fixed, but now I just wanted to show you a very important result, that breaking of degeneracies. If you take Planck and UV17 data, your tau and log 10 xi dot Reion, which, okay, I was lazy to put the pointers there, markers there, but these are here. So this one is 24.5 and the top one is 25.5. So you can see that there is a complete degeneracy between tau and log 10 Reion, and there is a degeneracy in the opposite direction at tau and this one. Okay. So if you use Planck plus QH second data, if you take all 3 of them, it actually constrains it here. So xi Reion is better constrained with using all the data. We tried to do another job, is that we tried to use a Gaussian process reconstruction. It is a machine learning method. Okay. So here we are saying that our model is based on several parameters or functions, actually which the distribution of which are actually multivariate normal distribution, and these are used in in science sector, industry sector a lot. Okay. So it works with a kernel function. It can be used for consistency test, and it can be to see whether the mean function that you are using is good, or you can also infer parameters from there. So this is what we did. We tried to check the consistency of single power law. I showed you, right? The UV luminosity density, they are used, some people use single power law, some people use double power law. Try to see whether double power law, single power law is good enough. And I'm not going to do the detail of the mathematics there or statistics there. I am showing you something here. So Gaussian process allows some variations in your mean functions. Let's say mean function is a constant mean function. The amplitude of the variation is given by sigma f, and the length scale of the variation is given by L. Okay. So this means this is the mean function that you started with, nearly sigma f equal to 0 and no correlation at all, or I mean here, this line actually. Now if our contour, this mean value is saying that it rejects this line, that means our assumption of the mean function was wrong. So this is a consistency check, that if I say that the luminosity density was constant over the redshift, this is not going to work with the data. Now if it is a single power law, with UV17 we can be 2 sigma sure, 95% sure that this is not a correct model. For double power law, it is working. Okay, so we use that for extrapolation. We do the Markov chain Monte Carlo. I can explain it later, so I do not want to spend much time on that as well. With UV15 and with UV15 here and UV17 data, which are obtained from different integrating the luminosity function to different truncation amplitudes, truncation magnitude. The results are there. The evolution of the electron fraction, and what you can find here is the summary statistics that you want probably. Again, caution that you should not just use summary statistics, but these are marginalized over different models. So tau that we find here is 0.052 plus minus 0.001 that we had obtained with other analysis as well. So using free form reionization history, these are the constraints that free-form model independent reionization histories, these are the constraints that you can achieve. The 50% reionization was done nearly at redshift 7, and the reionization duration 10 to 90% is nearly 2 to 3. So these are the methods, and these are the methods and the ways how you can join the data, different bits and pieces, and you can constrain the reionization history using CMB and using different astrophysical probes. So this is what I wanted to share with you. With that, I would like to stop and stop for questions. Thank you.
So you are using the neutral and ionization fraction in the first part of your talk from the observations.
Yes, ionization fraction.
Yes.
If you get neutral,
Yes.
you just say 1
Exactly.
minus that.
Yeah. So my question is, do you also account for the uncertainties in those parameters when you calculate the tau electron?
Uncertainty is this
In the
QH
XH1.
second?
Yes.
Yes, those are actually these are joint likelihood. What I do is that from CMB I get a likelihood. Okay, let's say it is chi-square, and from there also I use the error bars and calculate the chi-square, add it to that.
But
From
at redshift 6 there are only limits, because it's the dark pixel fraction gives you limits,
yes,
not the uncertainty.
Exactly. In those cases we use half Gaussian, where there are limits that we say that this is the 95% limits, and then other side we say that it is there is no limit. So
but most of your signal will come from the free electrons. In the post-reionization case, that's where your
post-reionization we are not constraining. We are saying that at redshift 6 or 5.9, this is 6, it is already over. So from there we are not using any constraints.
Right.
So
yeah, and the
that
second,
is where we are a little bit cautious.
yeah, and in the second part you are using the ionization equation dq dt.
Exactly.
It can overshoot, q can be greater than 1. If
There
you use
we are stopping the. What happens is that sometimes because I am using free form, I am allowing my differential equation as soon as it goes over 1, let's say. I'm stopping the differential equation. I'm allowing it to float, but I'm putting it to be 1. But at some point of time, let's say the source has dropped or something happened. Because this is free form, I'm allowing it to happen because my nodes are free, right? In that cases, if it goes below 1 again, I'm counting it for again.
Right.
So this
ideally you should account for the mean free path of the photon at that point.
This is something that we are trying to incorporate
it's already there in the literature in Madhav 2017.
Lyman limit system and few other things. Actually, we are doing this work.
Yeah,
we are putting some more physical inputs there as well. Thank you. Thanks for this suggestion.
So most of your reionization history suggests that end of reionization by redshift 6, but as a
this is not suggested by reionization. Okay, if you take CMB, it will not say that much. Okay, it can say up to some extent, but you are seeing that curve because all the other observation that I'm using, let's say QH second, they are all showing that after redshift 7 or 6.5, the electron fraction should be more than 0.8 at 2 sigma or something like that. So those things are also playing a role. It is not just coming from the model. It is
have you also considered the Lyman beta dark gap observation?
I am okay. So honestly, Lyman beta, it gives.
It gives a
constraint-
late reionization actually.
Okay, so what does it provide? It constrains which parameter here? Let's say QH
So-
second or
No, I don't. I am not sure. I mean, a paper I have seen. Girish is also a co-author of that paper. So that
can it be used to? Okay, okay. So I'll talk to you. I haven't used that. Thank you. Thank you.
Okay, as there is no other question at this moment, let's move to the next talk and thank Dhiraj
Thank you.
for this nice talk.